Hello, my name is Gennady Staskevich and I'm here to present a review of Revisiting Routing Control Platforms with Eyes and Muscles of Software-Defined Networking. The outline of the presentation is going to be introduction, background and context, Rfcp design, use cases, prototype implementation, and discussion. So the introduction, the objectives of this paper is to discuss the routing control platform in the context of OpenFlow and SDN, software-defined networks, to examine the concept of BGPs-based routing control platforms, and present controller-centric hybrid networking model called Route Flow Control Platform. So basically this is taking another look at the BGP or external BGP traffic controlling with software-defined networks. So this paper was presented in 2012 at the first workshop on hot topics in software-defined networks at ACM. The authors of these papers are Rothenberg, Nascimento, Salvatore, Correa, Lucina, and Razuk. So the motivation is that clean separation of function is paramount to any successful system, especially more so for complex systems like networking or operating systems. So the idea is to abstract functionality into separation of layers. It makes or separates it from hardware to the actual implementation, makes it much more intuitive and easier to manage. So software-defined networking effectively decoupled the data plane forwarding from the control and management plane functions. And the expected benefits are new services, feature velocity, and cost reductions. So motivation, a minimal attention to unutilizing software-defined for traditional IP routing and forwarding, so specifically the BGP traffic. This was one of the key motivations of this particular research. So the key ideas behind the software-defined networking are not new. Some of the very first ideas were actually part of the initiative that was about a decade ago called Routing Control Platform. And one of the reasons why it didn't perform so well, it was introduced too early. It didn't really have as much support as it does now, or interest, and the way that the software-defined networking was introduced was actually very wasn't really targeting the corporate or infrastructure where it would threaten the major corporations like Junipers and big data center providers, hardware providers, but it was targeted as a research platform. And then once it was shown how useful it was, it gained very rapidly a lot of interest from both industry, customers, and research community. So it focused on BGP decision to process and route control needs from operators' perspective of large networks. And the approach was to refactor the IP routing architecture to create logically centralized control plane separated from forwarding elements. So there are three base cases for the BGP deployment within autonomous systems. Typically you have a full mesh where every IBGP internal BGP speaker or a router talks to every other internal BGP speaker within an autonomous system. And then you have another approach, but that problem has scalability issues. The more traffic, the more routers and addresses you have within the network, the more complex your routing scheme becomes. So then you have route reflectors. They're more like inline filters. This is specifically so route reflectors were designed to address the scalability issue of maintaining the routing tables. But the problem is that these require a lot of engineering for to be effective, and can easily cause a lot of other issues if misconfigured. Then in between we have is a confederation, which is sort of like a combination of the both. It tries to confederation tries to partition or subdivide large autonomous systems into multiple smaller subautonomous systems. So recent trends to remove route reflectors and replace them with provider edge to provider edge encapsulated. Same concept, similar concept as in segment routing. This concept of IP encapsulation has been gradually extended to higher levels such as IPv4 and IPv6 Internet routing protocols. And in large networks, the control plane route reflectors are often placed in arbitrary core locations, resulting in suboptimal paths. Especially, yeah. So in very large networks, these route reflectors are very difficult to configure. In essence, a proposed route control platform solution is based on three architectural principles. Path computation is based on consistent view of network, so it offers a synchronized view or global view, or centralized. Controlled interactions between routing protocol layers, and expressive specification of routing policies, flexible and programmable. Essentially, the previous RCP work was constrained to iBGP and mostly within an autonomous system. But the focus of this particular paper is to investigate utilizing the OpenFlow and SDN paradigms or the architectures and apply it to the IP routing, the external eBGP speaking of applications. So there are three major parts to the routing flow control platform. This is what's being introduced in this paper. Is the hybrid networking model, the Rfcp components, and the use cases. So the hybrid networking model refers to the interconnection of both control and data plane of legacy and new network elements. So they're looking to how to ensure that the legacy hardware and in the new network elements, the new hardware that is OpenFlow enabled or SDN enabled devices, they interoperate. So the starting point assumes traditional model of provider. Excuse me. The starting point assumes traditional model of provider edges interconnected via iBGP. Added new Rfcp control plane, basically to control the control plane of BGP controller, and acts as a gateway, translating existing route reflectors into OpenFlow data paths. And the scale of such deployment can be dynamically programmed or adjusted by the network operator. The RCP is an evolution of previous prototypes. It's not a drastic or the new concept. It's just an evolution of many previous or much of the previous work. It's designed to accommodate mapping of virtual interfaces to OpenFlow enabled ports and ease the development of advanced routing oriented applications. That's one of the big goals, one of the big goals of the software-defined networking in OpenFlow is that it's supposed to encourage or facilitate the growth of new types of use cases and applications. So the Rfcp has three major components. The RF client, which collects routing and forwarding information generated by a routing engine, such as Quagga in this case. The RF server, which is a standalone application responsible for system's core logic event processing and ensure that it generates the consistent world map or the network map of nodes and connections. And RF proxy. So proxy basically all it does is simply sits on top of OpenFlow controller and ensures that they communicate correctly. So RFCP, this concept relies on a NoSQL database for maintaining logically centralized fault-tolerant database or the data store. The data store is composed of two main functions, the network information base and knowledge information base. So this is how the RFCP actually achieves the consistency or the consistent view across its entire autonomous system that it controls. The general information, so it maintains the RFC core state, which is they actually use MongoDB for this. It maintains RFCP core state, general information base such as statistical data, flow monitor, and administrative policies. This would be part of the knowledge base, and network information base would be part of our RFCP core state. So this provides consistent network view, both logical, physical, and protocol specific. And the communication model is using PubSub message queuing based on JSON based implementation of route flow protocol. The route flow protocol is used for connecting different modules with simple command response syntax. Northbound to RF clients provides a generalized abstraction of the OpenFlow specification version 1.x. So they do provide some generalization of the OpenFlow specification. Connects northbound to southbound, enabling programming of RF clients to OpenFlow based open virtual switches. Provides means for maintaining centralized state network programmability and flexibility. The use cases. So RCP has introduced some use cases like the original RCP concept, like flexible routing, security, and connectivity management. Efficient centralized global view enables many additional use cases for software-defined networks. And as we see, the authors of this paper introduce these are additional use cases. So engineered path selection, which basically enable per application tailored prioritized routing and load balancing. So you can focus your routing maybe on latency versus maybe just traffic lower priorities. Maybe some traffic could be lower prioritized where you don't really care if the ordering of it. So the other use case is optimal best path reflection. So perform optimal path planning as opposed to route reflectors. Path protection prefix independent convergence. So you can idea here is to provide maybe alternative paths where if say a router may fail, so you can do a very quick recovery from edge failures. You can also enforce data plane security, enable network processing and identification of potentially malicious traffic. Also perform secure inter-domain routing. Centralized model greatly simplifies the enforcement of BGP origin and other traffic routes, and simplifying customer homing and IPv6 migration. So the centralized, logically centralized view offers many benefits that can facilitate the development of these applications, and enforcing various policies makes it much simpler. And it seems to be like this is the newer trend again towards logically central, physically distributed but logically centralized or consistent views of networks. So the prototype implementation, the Rfcp route flow control protocol services are written in C++ as RF server modules. The RF proxy was implemented for NOx and POX open flow controller. RF clients work with Quagga, which is again Linux routing engine, and Xorb. Um, they both running in LXC containers. The data store is implemented using MongoDB for its scalability and portability. Um, they mention other popular NoSQL data stores such as Cassandra and some other ones. Um, so the derived descriptive grammar is written in Lex and Yek, and they implemented an aggregated BGP, calling ABGP routing service, where edge links are mapped to virtualized routing engine. So they demonstrated route flow with commercial open flow devices from Pronto, NAC, and IBM. They verified that BGP and OSPF interoperability with Juniper, MX, and Cisco devices, edge routers essentially. And they experiment this with traffic data at Indiana University, trying to so their objective were to simplify the network administration and increase network resiliency and consistency, given the large size of the university. So some of the things the authors pointed out is that Rfcp like systems could handle tens and thousands of eBGP sessions and perform hundreds of routing decisions at provider edges, so they can do in-edge processing. And this paper was released in 2012, so much more hardware or capabilities since then have been or became much more powerful. So this is indeed these numbers are I would say they're outdated, but software capabilities or software-defined networking has become much more powerful. Another thing is open flow processing in data path. So processing limitations within network devices is mostly due to unoptimized implementations. This is another thing that authors pointed out, that even in 2012, the processing limitation within open flow or SDN devices is mostly due to unoptimized and poor implementations. And high-quality data store-centric design provides enough foundation for achieving fault tolerance and many of the key benefits within software-defined networking, given such as the logically centralized view of a distributed network. So the potential advantages that Rfcp offers is that simplified edge architecture, lower cost, increased edge speed, power of innovation lead to different and potential new revenue models that may encourage new types of applications and different use cases, and again, which would translate into revenue models. Increases BGP security, stability monitoring, policy management by eliminating intra-domain BGP oscillations, facilitating centralized management of BGP policy. So again, centralization or at least logically centralized management of BGP policies would greatly simplify and make network a lot more stable and resilient to external attacks. So conclusions and work ahead. So authors argue that the presented architecture is an evolution of current IBGP-based route reflectors, and at that point I agree with them. BGP control plane is removed from both core and edge devices and abstracted higher level. So here's some final thoughts. It's not clear what is the overhead of maintaining a centralized data store and how much they actually store or how much overhead that they have. Also, how scalable is it under more realistic conditions? The use case that they had, they didn't really go too deeply into covering how much the data was or into the numbers. So it'd be really interesting to see how this would be simulated on a real large scale or realistic scale autonomous system. Another interesting point is that while MongoDB offers great performance, uh, at least according to more recent publications, Cassandra, also on a SQL data store, may be a much better choice. It has, for example, updates which you would assume that this the in-network uh, um, or at least large networks would see fluctuations in updates. So Cassandra offers much better performance for doing updates and has lower latency uh, in um, in various use cases. So I think in overall performance, I think Cassandra would give much better um, use case, or at least for this uh, Rfcp prototype. Also, MongoDB limitations is that if you're using a 32-bit system, then at most your total store can be up to 2 gigabytes per node. And also, each stored value of it or a document from the key pair in MongoDB is limited to 16 megabytes. And Cassandra basically is kind of like a natural evolution between, or it takes Amazon's Dynamo, that was paper, and Google's Big Table concepts and combines them together and released a NoSQL data store that is very fast, efficient, and as we've seen in Amazon's Dynamo and Google's Big Table, can scale to extremely large sizes, and actually at global scale, and and actually practical. So I think it would be very interesting to see this particular work by using Cassandra and actually benchmarking against Mongo, how well it would actually perform. Okay, and if you have any questions, please email me at stuskeg@clarkson.edu. Thank you.